Oh, no, she literally put it in bold statements.
Okay,
Yeah, I think so.
so
Yeah, always.
we are going to continue our lecture on arithmetic operations and different data representations. We were ending on integer addition last time. So we're going to continue with integer addition of signed numbers now, instead of just unsigned numbers. And we also have a guest lecture from Ollie today. He's going to talk a little bit about his research and how it's related to computer engineering. But so he's not coming here until 9, and he'll give a 20-minute short lecture. So we have some time to do this. So here, if we treat these numbers as signed, 2's complement representation, right? This is still 7, and this is still 7 because of the 0. And this is -7 because of the leading 1. And if we flip all of this, it would be 0, 1, 1, 0. Add a 1, then it becomes 1, 1, 1. So that means it's 7. So if we negate it, it becomes 7. So we know in its negative form, it's -7. Same thing with 2. 0, 0, 0, 1. Add 1 becomes 0, 0, 1, 0, which is 2. So the thing that we want to highlight here is if we do this addition with these numbers, we do 1 plus 1 is 0, carry the 1, right? 1, 1, 1, 1, carry the 1, 1, 1, 1, 1, carry the 1, and then 1, 0, 0 is 1, carry a 0. But then we get our result down here. It's 1, 1, 1, 0, which is, if we convert it, we see that it's 0, 0, 0, 1, add 1, it becomes 1, 0. Okay? So that would be a result of -2. But we want to see 14. But as we know, with the 2's complement representation and 4 bits, 7 is actually the largest number that we can represent. So that's why we have this overflow here. It goes from 7 to the -7 and then -6, and it reaches all the way back to -2. So we're going to cover how we can detect this, but one way that is an obvious way to check is I have a positive number, I'm adding a positive number, I should not get a negative result, right? So that's the simplest way to check. Same thing down here, I have a negative number, positive result. But there are better ways to do this check. But just before we get to that, so overflow is if the result is out of the range of your possible representations. So it can occur when you're adding 2 positive numbers. It can occur, so this is overflow if the sum or the resulting sign, the most significant bit is 1. You can have overflow when you're adding 2 negative numbers. So the overflow or the sum or result sign becomes 0. But when you're adding a positive and a negative number within the same representation, and the output is expecting the same representation. So by the same representation, I mean 4 bits plus 4 bits equals 4 bits. Then if they have opposite signs, you'll never have overflow. Because in order to get overflow, I have to go outside of the range of possible representable answers. But if I have 2 that are opposite signs within the same range, I can't go outside of the possible representation. So here is another way of checking. rather than just looking at the signs of the inputs and the sign of the output, like here, it's positive, positive becomes positive, we're good. And here it's positive, negative, so we know that it's always going to be good. But here we have positive, positive becomes negative, negative, negative becomes positive. Rather than doing that, we can just check the most significant carry and XOR it with the carry out. If this XOR is true, then there's overflow. If it's false, there's no overflow. So here, 0 XOR 0, this is 0, so no overflow. 1 XOR 1, again, this is 0, so no overflow. But 1 XOR 0, result is 1, this is overflow. 0 XOR 1, this is overflow. So I mentioned that we were going to be using this instead of just throwing it away. This is how we're using it. So we're going to take the XOR between the most significant carry and the carry out to figure out if there's overflow or not. But in terms of your result, you're just always throwing away the carry out. Okay. All right, so 2's complement integer subtraction. The way that we were going to implement subtraction, and this is true in hardware, is rather than creating new hardware to do subtraction, we're going to use the same adder hardware that we create and just negate the operand in order to do a plus negative b, which is equal to a minus b. So we can reuse the same hardware. So the way that we add this negation is because we have this 2's complement, we can just negate all of the input bits and add a carry in of 1. And that will be the add 1 to do our negation. All right. So overflow and subtraction. So if we subtract 2 positive or 2 negative operands, there is no overflow, right? But if I'm subtracting a positive from a negative operand, I can go beyond the negative threshold. And the overflow is, again, if the resulting sign is 0. And then that's because it goes from a negative to a positive. And if I'm subtracting a negative from a positive, that means I'm adding to that positive, and I can go beyond the upper threshold, right? And this is, again, overflow if the sign is 1, so it becomes negative. So here are our conditions, right? And so if we're adding, if A is positive and B is positive, if my result is negative, I have overflow. If I am adding again, if I have A is positive, B is negative, A is negative, B is negative. If the result is positive, then I have overflow. Subtracting, A is positive, B is negative, and A becomes negative, then I have overflow. If A is negative, B is positive, and the result becomes positive, I have overflow. But again, this is kind of the more complicated way of detecting overflow. For addition and subtraction, the XOR works. So this is what is implemented in hardware because it can be just checked with one simple gate. So that is addition and subtraction. Here is just a summary. I don't think we need to do a poll for this, but do answer the poll so we can do attendance. The code is 544. So just make sure that you complete that before the end of today. But we can do this together. So we have A plus B and A minus B. And the question is, can overflow occur if B is 0? Does anyone have an answer for this? Yeah.
One of mine.
You can answer this. I'm sure that your intuitive answer is correct.
I would say no.
Yeah. Because yeah, A doesn't change, right? In either of these cases, A doesn't change. So A is already being able to be represented by the current bit width or whatever the representation is. So it's not going to change, right? Because you're adding 0 or you're subtracting 0. The result just becomes A. So that's why overflow cannot occur. All right, so the next thing that we should cover is multiplication. So multiplication, just like the addition in binary, is the exact same way that you did it in grade school. So now your data representation is different. So if I want to multiply, this is 8, this is 9, right? I'm going to take this first one, multiply it by all of the bits of the multiplicand, and I get this result, right? 1 times 0, 1 times 0, 1 times 0, 1 times 1. And then for the next bits, I'm going to do the same thing, but shift to the left by 1. And the next bits, I'll do the same thing, shift to the left by 1. Next bits, do the same thing, shift to the left by 1. And now I just need to do this addition. So 0, 0, 0, 1, 0, 0, 1. So your multiplication is the exact same process that you already know. All right, so division. Again, this is the exact same process that you already know. So if I want to divide this large number by 8, I first look at the first digit here. If it's just 1, is 8 less than 1? No, right? So I would put a 0 here. It's just omitted. Is 8 less than 2? Nope. Put a 0 here. Is 8 less than 4? Nope. A 0 here. Now, is 8 less than 9? The answer is yes. Put a 1 here. Subtract 8 from 9. I get 1 as my result. Bring down the next bit. Now I ask the same question. Is 8 less than 2? No. Put a 0. Bring down the next bit. Is 8 less than 5? No. Put a 0. Bring down the next bit. Is 8 less than 10? Yes. Put a 1 up here. Subtract 8 from 10. I have 2. So my result is 9 with a remainder of 2. So we see that this is the exact same long division that you know already, but it's just in binary. All right. So the next thing that we should cover is floating point representation. So we went over fixed points, where we just have the decimal point that tells you the divide between the integer part and the decimal part. But with floating points, we want to be able to move that decimal around. And it's basically kind of similar to scientific notation that you, again, already have prior knowledge with. And it allows us to represent much larger numbers or very, very small fractional numbers rather than with having that fixed points. So here is an example of our notation that we already know. So if this is the number, if we normalize it and put it into scientific notation, we just have the first digits and then the decimal, and then the power of 10, which is dictating how far to move this decimal, either right or left, right? The floating point is very similar. So we have a sign bit to tell us if it's positive or negative. We have this implied one because we're always going to be normalized. So because we have the implied one, of the 32 bits that we're using for this representation, we don't have to specify the one. Then we have some bits to specify the fractional part. And we call this the mantissa bits. There are other names for this, but usually they're called the mantissa bits. And then we know that we're in base 2. So again, we don't specify the 2, but we specify the exponent value. So how far to move this left, how far to move the decimal point to the right. All right, so the floating point standard is defined by IEEE, and it was developed because of kind of divergence of representations. Now it makes portability for scientific code, because if we're all using the same standard, a lot easier to kind of use the same code across different applications. And it is now almost universally adopted. There's not many more representations used. Right, there's 2 representations. There's single precision, 32 bits, and double precision, 64 bits. Okay. And here is our format that we just went over. So we have the sign bits to specify the sign. So if it's 0, positive. If it's 1, it's negative. And then we have the implied one, the fraction, and then rather than just explicitly putting the exponent here, we actually have the exponent, but we have to subtract the bias from it. Okay. So here is the 2 formats. With single precision and double precision, 1 sign bit. With single precision, we have 8 bits of exponents. And with double precision, we have 11. And then the fraction bits, or the mantissa, 23 bits with single precision, 52 bits with the fraction. And again, the mantissa, or the fractional part, it's normalized. So that means we don't have to specify the 1 bit here. We know that it's always going to be there. So we don't have to include it down here. So we save 1 bit. And then the bias for the single precision is 127. And for double precision, it's 123. And that just allows us to not have a 2's complements representation in the exponents, so that we can have a little bit more range in the exponents. All right, so the first example that we want to look at is showing the binary representation of negative 0.75 in IEEE single precision formats. So the binary representation of this is negative 0.11, right? Because this is 0.5, this is 0.25, add them together, 0.75. So the normalized representation is negative 1, because we always want to have this implied 1, 0.1 times 2 to the negative 1, and that means that we move the decimal points over by 1 to the left. Right? So that gives us the 0.11. And this is our floating point format. So our sign bits is what? Our fraction bits. What would it be? Ten?
1/10. What is the fraction?
From this part. There's 23 bits. What's the first bit? It's just everything after this decimal point, right? So first bit is it's 1, right? Specify this. And then the rest of the 22 bits are all zeros. Okay, there's nothing after. The only thing I wanted to highlight is that you don't have 1, 1. You have this implied 1. You don't put it into the function. And then our exponents is going to be the exponents minus the bias needs to equal negative 1, and the bias is 127. So in this case, our exponent needs to be 126. So sign bit is 1. Our significand is this. So our mantissa is 1, 0, 0, 0, 0. Exponent needs to satisfy this. So it's 126. Okay. So here's example 2. We want to convert from binary to the representation. So sign bit is 0. Exponent is 128. So our real exponent is 1, right? And then the fraction is 0, 1, 1, 0, 0, 0. So if we put it all in, right, we're positive. We have 1 plus this, and we need to move the decimal to the right in this case by 1. So we get that our representation is 2.75 because it's the decimal is here, right? We move it to the right by 1. So to the left of it makes 2. To the right of it makes 0.75. Are we all good with this? Okay. So here is example 3. Which one of these numbers is larger? So they're both negative, right? So for A, we have the exponent is 63. So we subtract 127 from 63, and we get negative 64. And we can kind of ignore this for now, the fraction part. But for B, our exponent is 142. When we subtract 127 from it, we get the exponent is 15. So which one of these is larger? So actually, A is larger, right? It's closer to 0 because of its negativeness. Did you want to set up?
Yeah.
So we'll continue the rest of the representation and on Friday, and we'll also have time to work on homework on Friday. Did you leave?
I have it on my.
Computer. So as I mentioned, we do have a guest lecture from our department chair, and he's going to talk a little bit about his research and how it's related to computer engineering. And then can you just share the recording? The arrow button? I just do window. The window on the. Okay. Okay. And then the slides are. And then you can also minimize this so it's not in your way.
All right. Good morning, everyone. My name is Ali Ahmadinia. I am the other computer engineering faculty in our department. So I'm trying to give you a very brief overview of my research. I know we don't have much time, and I don't expect you to grasp all of the ideas here, but I just want to give you some direction. What was my research journey in the last 20 years, and what I have done, what I'm recently doing. And if you have any question in between, please feel free to interject and ask. So as you see in the first slide, the intelligent embedded system is the main area of research. So I don't know how much you have heard about embedded system in this course, but so when we are talking about embedded system, there are those systems that they are part of a larger system. So these are those type of computer products that we have in part of a larger system, and they are doing specific tasks. They have different characteristics, and we see it in every application these days. If we look in transportation, cities, buildings, large buildings, phones, even you see we have hundreds of small embedded systems within a car these days. So you can see here some of the main characteristics of the embedded system. Do you have marker?
It should be over there. There is one.
Well, you can see, as I said, thank you. They are part of a larger system. They usually providing some specific function for us. So we already know what exactly need to do, and we design and tailor the device to do that specific application. So they are not a typical processor, a GPU or general purpose processor. So when say GPU, the general purpose processor. So they are application specific, and they usually work with an external environment. They have sensors, they're collecting information, they have actuators. If they communicate, so we see when we see they are communicating and interconnecting in other systems, that's we see then another term rise that we call it IoT. Do you know what IoT stands for? Internet of Things. So if you have Internet of Things, are again those embedded systems that they are connected and communicating with each other. So it's the same thing, but it's just a matter of connectivity and sharing information in different ways with other devices or central device, base station, and so forth. Typically, they are working for a long, ideally, they are working without any termination. So they're always on, but they might have, in terms of, because if they are, for example, they are battery powered, they might have some sort of sleep mode. They go in sleep mode, but they're always something background is working. So we have always some sort of constraint. Either they are physical constraint, whether based on where you're using it. For example, if you're using a embedded system on a bike, so the size is very important, how much it weighs. If you're using it in a car, the reliability or the environment you're putting there is important. What type of environment is that? How reliable is that? And it can work in a harsh environment. And another big important part is the time constraints that we have there in the embedded system. So they need to be deterministic. So then we have always some latencies in the systems, and we need to know how much latency we have, whether we are meeting those specific deadlines from the system. So let's give you an example. So for example, you are designing airbag control system in a car. So when for example, the driver has an accident, you want the airbags to be released. So you have some time constraint there. So you want to release the airbag maybe within microsecond or millisecond, not within 5 seconds. If it is 5 seconds, it's catastrophic. So we have those type of constraints that make it real time. So you need to make sure you meet those deadlines. So these are the things that we need to consider when we are designing embedded systems. So if you look into the processor boards, computers, we see computers everywhere. But what we have heard mostly as in computer science or even in computer engineering, we always talk about desktops, servers, and we do a lot of research on that area. But if you look into the production of the processors, most of the processors that we are seeing, more than 98% of them are in embedded boards. You're using them in devices in a larger product, and they are doing specific applications. So even if you're looking at your mobile phone, all you hear that you have always a big processor, A processor, A7, A8, or A9 processor there. But there are also there are multiple smaller microcontroller and processor within that mobile phone to deal with different functionality, for example, to deal with the communication side of things, or for they have also for different type of drivers that they need to handle. So, as I just said, embedded system has been used everywhere. Obviously, there is a lot of growth in this area, and you can go in different directions. So it is just a brief overview of my research journey, what I have done the last 20 years. I work in the area of reconfigured computing, which is more about the FPGAs. Have you heard of FPGAs? So how we can configure those devices. And then also I work on system on chip, network on chip, Internet of Things more recently, and Edge AI. So I'm just trying to give you a very brief overview now. Okay, so thank you. So in the area of, when I started my PhD about 21 years ago, the work I did in Germany, I worked on a project, we call it Recon. So in that work, we did some work on the FPGA, how we can manage the resources on a partially reconfigured FPGA. So in those days was the first technology came out that you could, you know, I don't know how much you have heard about FPGA in this class. So FPGAs are a sea of gates. So you have a lot of gates, logic gates. We call them processing element on a device. So typically the way we always design a circuit, and so we just configure it on this device, on the FPGA. In a partially reconfigured FPGA, what we do, we can configure part of that device while the other part is still running. So that was something new in those days, that we wanted to come up with a system can manage all of the resources more efficiently. And we use on the Reconote project. Could you put the next slide? So what I did, we designed an operating system within the FPGA that could manage the scheduling of tasks, placement, where we place them, how we're going to route between these modules online and on the fly when we are partially reconfigure the device. So, and we, could you the next slide? So we also did prototype a platform for that project, and we designed, because again, the way that we had this type of partial reconfiguration, especially on Xilinx FPGAs, were column-based. So we could just change the bit stream in each column separately. So we designed as a system, you can see here, for each of these slots, we could configure each of them separately, and they could communicate through a crossbar and a bus here between them. So then I moved on and I did my postdoc. I moved on to working on a system on chip and designing high level systems that we can model them at high level. So we use System C to model different modules. And then we do the kind of design space exploration, how we can use the best configuration to put them together based on the type of communication we use, based on the type of setting we use in each of these modules to get the best area footprint, to have minimal area footprint or best power consumption, and also meeting the latency that we need. So we wanted to make this design space exploration much faster. So we designed this system level modeling, we call it SOCAD. So we come up with we focused on the targeted wireless applications. So mainly we will focus on the supporting different wireless protocols, and we designed different parameters for the FFT we use, VTRV decoder, and we also the processors that we need to use to control them. And then we use our system, our framework to generate for us the model when we have this system, the model of each of these IPs, and it's going to create for us the whole system, and also integrate it with the communication IP that we needed to use for that. So it helped us to build a system with multiple components that we have already at a higher level, and then create that. So this could help us with saving a lot of design time. We didn't want to design for every configuration from scratch. So that helped us to have these IPs separately, and then the system would integrate them for us and also generate the code and provide the whole system. So we see a very similar approach now in the ARM business. So have you heard of ARM? ARM processors? What does ARM stand for, do you know? Is Advanced RISC machine. So these are the machines that they are using a reduced instruction set. Computer. So ARM also follow the same business model. So they are providing IP for different processors, different modules now, and they don't manufacture and fabricate the process. So when you're using, for example, iPhone, Samsung, all of them, they all have an ARM processor. So Qualcomm, they use the ARM IP library to use their IPs to generate the whole system integrated, and then they manufacture, fabricate their system. So it was similar to what we see now in the some of the companies like ARM that they are using the same. So you can see a snapshot of the system we designed, how we could change the setting for each of the IPs that we had there, choose the type of communication we wanted, what type of constraint we want, and then it would generate for us the whole. So I also worked when I became a faculty, when I was teaching as an assistant professor, I work more with the industry in more applied projects. I work on the embedded vision systems, especially I worked how we can do real-time particle analysis in oil pipelines. So, you know, for example, when we have this oil pipeline in deep sea, they want to make sure they always monitor what type of particles in there, if they're causing any problem in the system. So in those days, we didn't have much machine learning. So we relied pretty much on signal processing techniques, filtering to segment the foreground and background of the image and find those particles and send alert to the system. And then also I worked on the multi-core architecture. So because again, at those when we had more resources, when we had more processors and cores within the chip, it was become more important how we can manage them. So I mainly work on the area of the 3D network on chip when I was in UCI during my sabbatical, and then also I work on the secure communications of the hardware security of the communication between these cores as well. So network on chip. So when we are talking about network on chip is a communication medium that we use, how we can communicate between different cores or processing element that we have in the chip. So a typical way that it has been mostly implemented is using a network. So a network on chip is a two-dimensional network on chip, and we have routers that help us to communicate with the network and send information between these processing elements. You go next slide. And then because it was again taking a huge overhead in the system and had a huge footprint, then the idea of having a multiple layer chip was emerging. It was about 10 years ago. And then we come with the idea of the 3D network on chip, and many people work on that area. But again, the 3D network on chip has also its own issues. So when you're using a 3D network on chip, it makes the communication faster. It has much less delay because you don't need to go through all of these hops, go from one processing element to another processing element. But again, using those type of vertical links can be very expensive, and they might not be used efficient. So the main idea was that to generate a 3D network on chip with minimal number of 3D communications, so vertical communications here, but at the same time provide a comparable performance to a fully connected or regular 3D network on chip. So we work on optimizing regular 3D node systems. So in order to come up with the best patterns that we could use, we did a lot of investigations. So we had a simulation system that we look into the average link utilization, how much each of those links in a fully connected system would be used, how much in vertical links would be used, and how much the buffer would be used when you have a uniform traffic in a fully connected network. And based on those utilization, we designed the patterns where we wanted to place those 3D connections, those vertical links connections in a 3D chiplet. So here you can see the design flow of that system. It was a combination of the 2D and 3D routers. And we choose what type of traffic we wanted to use, and we had a full simulator to help us to look into the link utilization based on the traffic we use, and then generate for us the optimized architecture based on the input traffic that we had. So again, to the snapshot of that system. So one other area was also is very important that I become much more interested about the security side of the chip design. So how we can make sure when you have multiple core on a system and they are working on different type of application, different users, even in some cases, how we can make sure those communications are secure and it's not compromised some of the communications that we have within the chip. So we come up with a concept. We called it hardware sandboxing. So we could kind of, similar to virtualization, we see in the software these days, virtual machines, we created a virtual or a sandboxing within the chip itself. So we wanted to make sure that all of the communications here are completely isolated between each of these cores, and that was one of the main projects. So looking at some of the more recent projects I have worked on, so I worked on the Clean Air project. It was an indoor air quality. Go next slide. So this was a project about 6-7 years ago with a group of undergraduate students here. So we designed a system that worked with multiple controllers. It was an Arduino board, had multiple sensors, and we also implemented a neural network on top of that, RNN neural network. If you go to the next slide. So we tested how we can make sure this device can control the information about the temperature, heat, and the cooling setting of a HVAC system, and based on the information received from the gas sensor, give us the best setting that we need to put in the HVAC. So we use a real neural network, and this is a type of neural network they're using just the value of 0 and 1. It was very efficient for implementation of microcontrollers. And we also did some sort of intrusion detection analysis on that as well to find if there are some anomaly in the system, how we can detect it in these systems.
I have a question.
Yes, go ahead.
In your model, 2 slides back.
Yeah.
I noticed that you're having it communicate with the cloud. Wouldn't that cause like a bunch of, like time delays because they're gonna have to.
That's for
process-
sure. Yes, yes, yeah. There was delays there as well when we wanted to implement. So the way it worked, it first not send all the information directly to the cloud. It was sending to an app on the board, on the mobile phone. So we use the Bluetooth to send the information. And again, it is not the amount of data here is very small. So it is not a huge amount of data that cause a huge delay. And we don't have a real-time concept that you need to meet, for example, within a millisecond. Even a second delay here doesn't make much difference here.
Because it's humidity, so humidity, we're not expecting to change very much, very fast.
So some of them, again, another project we did, we are working with a chemistry professor here is on how we can realize virtual reality lab in science. So for example, we can use the VR headset and handle different lab tools and follow them and provide feedback to the user, how they have used the lab tool, whether they're using it the correct way or not. So the way that we can track this type of information is either using the passive method or active tracking. So in the passive tracking, we are putting some markers on these devices, on these lab tools, and follow them. But the part that I was mostly involved was the active tracking. So we didn't use that. We didn't use those markers on these lab tools to look at the camera to follow them. We used active tracking and putting sensors on these devices and see based on the values that we are getting from the sensor to determine the location and movement of these lab tools. So one device that we have designed, we call it the Ugly Duck. It was a 3D model that we printed and we put 12 sensors on that, and we tested the Steam VR to see how accurate this system is. And what we have done is much cheaper than what we see the Steam VR provides. So the Steam VR system is about, and at that time we looked at it because what $700. Just that was one of the markets, but we spent about $90 to build this system. Right. So looking more recent work again, Edge AI. So I don't know if we can cover everything because some of you have class, but I just want to maybe mention a couple of things about Edge AI and then So I mentioned about the IoT. IoT said that is the connecting when you're connecting these embedded devices. So when you have these IoT nodes, they have multiple nodes here, and all of these nodes need to work with cloud, right? So typically, when you're wanting to communicate all of them with cloud, is not very scalable, and also it takes a lot of time to communicate, and they might not have the right communication protocol. So in order to create a more scalable system, we use edge computing. So we are using base stations or edge devices, and these edge devices, they can also work in the proximity of a set of these IoT nodes, and they can provide some of the services they need, and then they will be connected to the cloud. So this is called edge computing. And edge AI is that we are providing how we can manage the AI or machine learning at different levels. We're not just doing it at the cloud level, we might do it at the edge devices and sometimes at the IoT devices and that stuff. So this is a very big area and very important area of research, how we can implement AI and machine learning in a distributed manner at different levels, at different type of platforms, and how we can make sure we are meeting those type of constraints that I mentioned before. So I'm not going to go into details of all of these slides. I want to respect your time, but just to give you an idea, for example, here was a multi-view image recognition. So we had multiple camera that they are grasping images from different views, and we are using a edge device to do the diffusion here for us to provide us how what type of recognition we can do on those type of objects that we are looking for, and then also migrating some of the work if some of these smart cameras they are, for example, on low battery, how we can migrate some of these work to make sure all of them can maximize the battery level. So it was a kind of edge orchestration architecture. I'm not, it was a very brief and a lot of information. I'm happy to discuss with any of you who are interested to work in these areas. We are working on multiple projects on Edge AI. We have also funding in this area, and I would be excited to work with every one of you if you want to be involved in those type of projects. And I have office hour usually on Monday morning. If you cannot make that time, just email me. I always can make an appointment for you to drop by and discuss if you have any interest to work in these areas. Thank you. I know if you have some classes you need to go, please feel free to go. But if you have questions, I will be around to answer your questions.
And also just make sure before you go, answer the poll.
Oh, what's the code for the poll?
544.